So thank you for joining us in the previous video segment on the classroom discussion on how Seaborn plays a role in data visualization, how it's really very, very helpful, even though we are just talking about two functions in Seaborn. Now that we have spent a lot of time understanding the various usage aspects of Seaborn, let's really go over to the spider lab, and this is where I need you to run your spider and we can work out the codes to generate real graphics. Now again, as a quick um, intro, actually I already introduced, but let me just make a quick reminder. You want to click on Tools, IPython, and check on the Graphics tab to see that you have the inline, all right, the inline being set. Well, this inline is going to make sure that the graphics are produced inline. That means within the console. As we type the command, the console also has the graphics being popped up. And at the same time, when this is set to inline, you will also get to see a gallery of all the charts being drawn here. So it's quite convenient to select the thumbnail. Right now it's blank, but later on it will be filled up. As opposed to if you set to automatic, then a new window will pop up and then we can do some sort of interactive movement with it. Not a lot, but decent ones. And but that would just mean that you have to flip the screen windows back and forth. There are times when one is better than the other. For now, I'll stick to inline. Okay, good. So let's begin by importing the relevant libraries. We need NumPy and Pandas as before. And we learned that Matplotlib's PyPlot is definitely the drawing engine that is needed. And Seaborn is built on top of that. So we need to import Seaborn. And the common shorthand alias is SNS. So let's use back that. Then we want to define a data frame. So by now, I hope you're very familiar with this. We're just doing the same data frame as in the slide. Column A having these numbers. So this is column-wise kind of a setting, but typed out horizontally. So this is very user-friendly for us in terms of listing the numbers manually. So we have the data frame, and now we want to create a heat map, all right, of this data frame. So let's do that. And I've, of course, also included the Seaborn documentation on color palettes. Really nice, bit of science there as well, to be able to smartly choose the right color palette. So have a read in that URL. We create a color palette, yellow, orange, brown. As a CMap is true, just creates the proper object for us to substitute here. So let's just see what we get from here. Exactly the heat map, right? Showing this interesting cell, B6, column B, row number 6. If you don't like this 0, 1, 2, 3, 4, 5, 6, just decorate the df dot index with something else, and then you will get to see them. So very, very simple and easy to use, and therefore our responsibility becomes how to choose an appropriate heat map color. So the color map. If the color map is not nicely chosen, it will not produce something that will be visually impactful. That means the interesting cells will be very properly and brilliantly colored to attract our visual attention. Then it will lose it will not partner our eye apparatus in a very meaningful way, and then it will lose the whole point of the exercise will be gone. Okay, so let's create a new figure, and then we'll do a dot core dot replace. Remember, this will replace the diagonal ones to zeros, and then we plot a heat map to use cool warm, and I suggest you just use this for correlation displays. Very red means high temperature, so very large correlation, strong positive linear correlation. Very cold will be very blue, ice cold, and so it'll be very negative, -1, very negatively, strongly negatively linear correlation relationship. So let's draw this, and correctly we see a correlation like that, right? So a mild correlation kind of occurred here between D and B, a pretty mild but big enough to be 0.2 thereabout. We can always find out from the actual correlation matrix itself. B and D will be 0.34. All right, so mildly strong. Certain social studies 0.34 correlation is considered wow, it's like wow, so exciting, so strong. I wasn't expecting anything, right? Um, between the number of candies I gave to my child and his GPA performance later on in the university. so so if really you get this is amazing, isn't it? So we from the correlation, even though eyeballing wise we might miss it, the chart, the correlation chart, definitely attracted this our attention to it. Next, let's quickly draw a pair plot. In a new diagram figure, pair plot, finish, and see what we get. What do we get out of pair plot? Now it will take a little bit of time for the pair plot to compute because obviously it's so massive, right? There are so many scatter plots and histograms to make. But then having a quick look, the axis value is not so important, but a quick look, not much of a pattern we can detect. So we'll leave it as that. Yeah. Okay, now let's pretend to prepare the DF2 data. So I just copy and paste it from the slide using NumPy's random number generator, right? So if you recall what I discussed about NumPy's random seed function, everyone, if you tune into this, you set seed to 1, 2, 3 now, all right? And if you do np random dot normal of 5, 2, 10, that means give me 10 numbers of random numbers that follow normal distribution with a mean of 5, standard deviation of 2. Then when you check your screen, you will see that all your numbers are the same as mine, even though all the numbers are random. So this is what the seed does, right? It's tuning our random number generator to the radio station having 123 megahertz. All of us will listen to the same content. All the content seem random and generated in real time, right? So no prediction of what's coming next, and yet everyone hears the same content. That is what it does. So we're going to generate 200 numbers. That's a lot. We can always bring it to 2000 easily here. Um, and we have 4 columns. And we purposely handcrafted linear relationship in Y with X and non-linear relationship between V and W, right? So this is a parabolic. So that is our DF2. We just run it first. Okay, and we say what's our DF2. All right, lots of numbers, and even if we look at it, we are not sure what we are looking at. So what do we do? So in the face of such a huge problem, right? So 200 rows and 400 columns, maybe we have 4 columns, but there could be more. First thing we should do is to run a pair plot. Okay. So in a new figure, perform pair plot. Don't talk to me first. Let me run pair plot. And this is quite big. Let me clear the graphs and let's run it. So it's going to take some time. Depending on how fast your computer is, it should take a couple of seconds, right? So okay, that's quite fast. And this will be our pair plot chart. And straight away, we see something interesting, right? So that seems to be a negative line here. Is it a line? Is it a curve? Can't tell. But this is a line, right? This is X and Y, it's linear. And let's confirm with our linearity test. So after pair plot, the next test is any linear calculation and linear pattern. So correlation will be a strong linear detector. It's like a Geiger counter. Is that radiation? All right, but if there's strong X-ray, Geiger counter won't react, even though it's very lethal to us if we exposed under prolonged exposure to X-ray. But Geiger counter will not register, right? So same thing. If we see strong correlation, we can't tell whether there is other relationship like curve relationship. But having seen all possible relationships, now we can really tell that V and W actually is a curve, or maybe it's a line. Let's use the line detector, right? So then we can use the correlation to find out if what we perceive as a curve, maybe a line thing, is actually a line. Okay. So yeah, correlation says you can pretty much treat it like a line because it's exhibiting strong negative correlation with the deep blue colors. Okay, so you might say, but wait, I thought it's parabolic. You're right, because when we generated it, we use parabola. But this part of the domain, that means the range of the v and the w we are talking about, is like one arm of the parabola, right? So this arm here, if we don't complete the parabola, can we approximate it with a line? And the answer is not bad, right? Not bad. So we would then perhaps consider, using a linear regression because it works with the line. Okay, good. So that basically concludes our illustration on the two very powerful functions offered by Seaborn, which will be the heat map and also the pair plot. Okay, so remember these two, and I hope you have fun using them to help in your data analytics calculations and maybe your career. See you in the next video.